Here's a car going over a hill problem. It says the dot at the right, below the picture I put on the side here, represents the car on top of the hill. Draw a free body diagram showing and labeling the forces, not components, exerted on the car. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. Each force must be represented by distinct arrows starting on and pointing away from the dot. So even though it's not in the picture at the exact top of the hill, I'm going to draw it on the exact top of the hill right here. So we will have two forces here. One is as it sits on that hill, we will have a normal force, which I'll call F sub n there. And then we will also have, because it's here on the planet Earth, a force of gravity downwards. I'll call that F sub g. So how do I know? I've clearly drawn the gravity longer than the normal force. How do I know that that's the case? Well, if it was just sitting still right here, then the two would be balanced, just like a car sitting on a flat table. They would be balanced out, the gravity and the normal. But as we come over the top of the hill with some speed, you're going to start to lift up a little bit off of the hill. So as you come up here, you're going to be just a little bit of that feeling that you've had on a roller coaster if you've ever gone over top of a hill too fast, that oogly feeling. And so that must mean that you are starting to rise up a little bit, and the normal force must be dropping until you start to lift off of the actual tabletop there. So we're going to use this now, this picture here, to build. I'm going to keep it there for just a second, because here it says, starting with Newton's second law, derive an expression for the maximum speed v the car can have without losing contact with the road. For each line of your derivation, explain what was done mathematically. In other words, annotate your derivations. Your expression should be in terms of capital R, which is the radius, and physical constants. So I can just get started here. I'm going to use my picture here, my free body diagram, and as we always start these, we say the sum of the forces must be a centripetal force because the car is going in a circle. And if we look at our picture here, the center of the circle is down here. So everything that's towards the center is a positive, and everything that points away from the center is a negative. So the force of gravity minus the normal is the centripetal force. So, and what I'm saying out loud, that's what you should be writing on those lines, annotating your derivation there. So next thing is, just when we start to leave the top of the hill, that normal force, that would just go to zero. The moment you lose contact with the hill, there can't be a normal force. So that part actually drops out and goes to zero. And so now the force of gravity alone is supplying the centripetal force. So we go and we plug in here. We have mv squared over r. I'll write it as a capital because that's what they do this time. Sorry, this side goes over there actually. And then the force of gravity is mass times gravity. So those two things cancel out. Solve for the v right here. So v then would be equal to the square root of the radius times gravity. Notice that this actually turns out to be the same as the ball going in a vertical string final conclusion. The only difference is for the ball going in a vertical circle, that would be the minimum speed before it fell out of the circle. This is now the maximum speed before it leaves the top of the hill, leaves the circle. So that's a max instead of a min. In your derivation, explain why the normal force was set to be zero. Well, we already talked about that, because if you go too fast, gravity won't be able to supply the normal force to keep you on the hill, and you'll fly off the hill, and there can't be a normal force if you're not in contact with it. And this one we've actually already answered too. A truck of mass 2m is on the hill. How's that velocity that we just solved for going to compare to before? Well, it doesn't matter. The mass is canceled out right here, and they weren't in the final equation. So that's true for any car, no matter the mass. A more massive car has less gravity pulling in the circle, or more gravity pulling in a circle. But a more massive car also is harder to make to go in a circle, and those two effects cancel out.